Hello everybody. Welcome back to the Joy of Coding at Portland State University. As we learned about in the previous screencast, relational databases persist data using standard language and concepts. Now let's talk about how Java programs can work with relational databases. So there's a Java API called JDBC, or Java Database Connectivity. And what this provides is a standard interface, a standard Java interface, through which relational databases can be worked with. The JDBC API comes from the java.sql package, and it contains the classes and the interfaces and the exceptions and all the code that you'll need to work with relational databases. Here are a couple of the key APIs in that package. There's a class called Driver Manager, which connects to the database via a URL. And we'll shortly learn what a driver is and how to access the database using it. That Driver Manager returns a connection object, which represents the session that the client program, the Java program, has with the database. And when a program has a connection to the database, it can execute statements that represent, well, SQL statements, right? This is the select and the update, those kinds of things that we learned about. When you execute a statement, you get an object called a result set, which tells you the result of the operation. Was it successful? What data did it return? Things like that. And if there's a problem that occurs while working with the database, an SQL exception is thrown. And so when it comes to working with SQL databases and Java, these are the APIs that you're going to need to know. And the nice thing is that these APIs will work with all kinds of relational databases. Like I said, JDBC is a standard API, which means that you as a Java programmer only need to deal with one set of APIs. But the reality is that each database has its own implementation of the database operations that it performs. And there needs to be a bridge between the two. And the bridge is something called a database driver. And the idea here is that every vendor provides a driver that allows JDBC to be used to access the database. That Driver Manager class that I mentioned on the last slide is the thing that knows how to create a connection to a database based on its URL. Now, the URL looks a little different from the URLs they probably used to just by working with the web. It's not an HTTP URL, it's a JDBC is the protocol. So they all begin with JDBC:. And then there's also a subprotocol for these URLs that are used to connect to databases that specifies essentially a database vendor. So you'll see something like JDBC:MySQL. And then after that is the address for the URL, and that specifies how exactly to connect to the database, or really the kind of location of the database to connect to. And this is vendor specific. So sometimes you'll have like a host and a port if it's a remote database. Maybe it's a file location if you've got a database locally. Sometimes there's configuration about the database instance name or how SSL communication is enabled, things like that. So even though the JDBC API itself is vendor neutral, the connection string is a place where you end up putting vendor-specific information. But it's only in isolated places like that. So here are some examples of those JDBC connection strings. So as you can see, they all start with JDBC, and then they have various vendor names next to them, and then each vendor has its own syntax for connecting to that database. And here's how the Driver Manager API works. It's really quite simple. You have a getConnection method on the Driver Manager class. It's a static method. You give it a URL, and then it's up to the Driver Manager to find the appropriate driver and then pass the connection string onto that driver, which will ultimately connect to the database and return a connection object from the JDBC API with which you can interact with the database. Let's explore what a connection object is all about. So the connection itself is, well, it can take a while to sort of get up and running, right? Sometimes there's network handshakes involved. There might be authentication, lots of stuff being passed back and forth. So the connection itself can be relatively expensive. And so this is why if you have a large application, what you want to do is pool your connections, meaning you reuse your connections after you're done with them. And so then there are libraries that you can use that will pool the connections to the database to make it more resource efficient. Now, you may recall that in the previous lecture we mentioned something about auto commits when it comes to transactions. By default, your JDBC connection will be auto commit, meaning that every time you execute an SQL query, it will be formed in the database. You don't need to worry about beginning or committing transactions. If you do want to manage your own transaction, then you set the auto commit property of the connection to false, and that will instruct the database that it will, a transaction is required in order to interact with it. And the way you commit or roll back your transactions is by invoking the commit or rollback methods there on the connection object. So if you're working with transactions, connections really become pretty important. Connection also has a method called getMetadata, which will give you a description of the database, the schema of the database, in an object called database metadata. So that's where you can find out about the tables. You can figure out what kinds of keys it supports. Does it support outer joins, stuff like that. Now, note, because a connection represents a connection with a resource out there, it's important to take care of them and to close them out when you're done with them. So as a result, the connection class implements the auto-closable interface. And so it's got a close method, and in a number of the examples that you'll see, we use that inside one of those try with close, one of those enhanced try blocks, so that you create the connection, you perform some operations with it, and then it'll automatically be closed so that you can not worry about resource leaks within your program. So from the connection, you can get an object which implements the statement interface. And a statement is an object that performs an operation on the database. Just like connections, statements are also auto-closable, which means that you can use them in a try-catch block. Now, statements offer three methods for executing SQL. There's execute query, which will run a select statement and then return the results of the select statement in an object called a result set. There's execute update, and this implements the other CRUD operations like insert, update, and delete. And what it does is it returns an int for the number of database rows that are affected by the statement. So you can say, great, I performed delete operation, and here's how many rows were deleted. And there's also a general purpose execute, which can take any SQL statement and that returns abstraction over that. And this is a nice general purpose tool if your particular piece of code doesn't know whether or not it is executing a select, an insert, an update, or a delete. Statements also have support for batching SQL statements. This is a nice optimization when you're performing lots of operations on your database. Databases know how to optimize batched operations. Basically, you take your statement and you precompile it and then send a bunch of data to it. It's more efficient that way. In this course, you won't be dealing with that kind of scale, so don't worry about it. But it's something that I want to let you know about because it's something you might encounter when working with relational databases. As I mentioned, the execute query method returns a result set. So the result set is an object that has the rows, information about the rows that match the query. The API, the interface, the Java interface for result set looks a lot like an iterator. So the result set object knows what row it is currently processing, and then you ask it for information about that row. And when you're done with that, you can advance to the next row using the next method. So essentially, it's got a cursor that it maintains and provides information about whatever the cursor is pointing to. While you are inspecting a row that came back in the result set, you can get information like, hey, give me the int value that came from this column, or the string value that came from that column, and that's how you get the data out of the result set. And again, result sets, because they maintain a connection to the database, they must be closed when you're done with them. Otherwise, you're going to have a resource leak. So here's an example of some Java code that uses the execute query method to query the database using a select statement. So here we're going to select all of the information in the courses table, so the ID, the title, department ID, and the credits. We got ourselves a connection to the database previously, and we're going to create a statement for executing that SQL by invoking the statement method of the connection. That gives us a statement object, and then we can execute the query by, invoking the execute query method. That'll give us a result set, and then we iterate over it. So we use the familiar while loop syntax here. So while there are still additional results in the result set, give me the next one, and then read me the value, the int value that's returned first. This would correspond to the ID. which you call getString for the title column, etc., etc. So we learned about the various types of columns that are available in SQL, and JDBC maps those column types to Java types. So we saw an example of this in the previous slide where we had statement.getInt and .getString. Well, here's more information about that. So the getString method from a result set will return a string for SQL columns of type varchar or text. Basically, well, all text data is a string. For 32-bit numbers in SQL, like integers and ints, there's a getInt method that returns a Java int. For decimal and numeric, this is where you'll get a big decimal. Again, big decimals are floating point numbers that have fixed precision. Bit and Boolean types in SQL are represented by little boolean in Java. And for date and timestamp types in SQL, there's a getTimestamp method from result set. And this returns a type that's probably new to you called Java SQL timestamp. So timestamp is an older type. JDBC has been around for a very long time and actually predates the java.time classes that we learned about. This is like, local date time and zone date time, things like that. So at the time, SQL introduced its own timestamp class because SQL includes nanoseconds, which Java didn't at the time. So timestamps are a lot like old school Java util dates. They represent a point in time with no time zone, and so then it's up to you to have to manage that. But the timestamp class has been augmented over the years to have compatibility with java.time APIs. So you can there's a from method where you can take something like a java.time local date time and from it create a timestamp. And similarly, there's a to local date time which will take a Java SQL timestamp and return a local date time for it. So as you may recall when we talked about identity columns, these are columns that are populated by the database itself when the row is created, almost always used for primary keys. You might need to know this information when you create some data. So let's say you insert some new information into a table and then you want to get the ID for it so that your Java program can store that ID, can use that ID for other things. Here's an example of how to do that using the getGenerated_keys method from the statement object. So here we're inserting into the courses table. Here's a new course that we're adding. And when we call the executeQuery method on the connection, and we give it in addition to the SQL parameter, we give it the returnGenerated_keys constant. You can then invoke the getGenerated_keys method on the statement object to return a result set that has all of the keys that are created when the value is inserted into the database. So as you've seen, SQL, it's a programming language. You can do a lot of stuff with it. And like any programming language, you're basically telling a computer what to do. And so databases will follow the SQL that you give it. And this is great when what you give it is happy path XML that does what you want. But because it's so general purpose, it's very easy to either inadvertently and also purposefully create SQL which is malicious, which will do bad things to your database, bad things to your application that you as the author do not intend. So you need to be really careful when you craft your SQL statements. So consider some Java code like this. We are logging in an employee. And hey, we've got some employee database, and we'll create an employee object from it, whatever. And so when you can imagine this is code that backs a login page to your web application. So you put in, you have the user put in their username and their password, and they click submit to log themselves in, and then somewhere in your code you get down to the following login employee method. And so what we're going to do is we're going to go look up the employee based on their name and their password, which is all stored in the database, and from it create an employee object that then is returned to the application and will be used as the employee uses the application. So we're going to go and select all the columns from the employees database where the name of the employee is what was passed in there into the method, and the password matches what was passed into the method also. And so we go and create our statement. And then, hey, let's say we've got some method that creates the employee object from the results of executing that query. Good stuff. It probably works well. But consider what values might be passed in the real world for that name and password parameter. So, they might come directly from the user, right? The user, types in their username, and that same value might just be passed through your program to ultimately where it gets here. Well, what happens if someone is mischievous or malicious and puts in values like admin quote space dash dash for the username, and then foobar whatever value for the password? Well, if you look at the code up above, we simply just take Java strings and concatenate them. So you'll end up with SQL. It looks like this: select star from users, where name equals admin end quote dash dash and password equals foobar. That dash dash is a comment. So all the database is going to execute is the query select star from users, where name equals admin. So as a result of this, malicious content and our naivete when creating this SQL statement, the user is able to log in as administrator without knowing the password, because the password criteria in the SQL statement is ignored. It's in a comment. This is not the query that you intended to run, and yet this is the query that has run, and all of a sudden now anyone can log in as administrator without knowing the password. This is a simple example of what's called an SQL injection attack, where your program receives data from the user which is maliciously crafted, or at least mischievously crafted, to have your program behave in ways in which it was not intended. So this is bad. What can we do to fix it? Relational databases and SQL support something called a prepared statement, which allows the database to do some extra checking and then also optimize on an SQL statement that is parameterized for multiple uses. So here, what we do is we have a statement that it basically is a template for a statement. So here we do something similar to our other queries, where we select information about the courses in the courses table, where department ID equals question mark. So this is the SQL that is sent to the database. And it's saying, hey, listen, this is the prepared statement. This is the parameterized statement that I want you to execute against. Similarly, we could use a prepared statement for the query from the previous slide. We're say select star from users, I think his name was employees, that's a typo, where name equals what's ever passed in and password equals what's ever passed in to the database. And because the database works with these prepared statements, it can be smarter about detecting values that don't belong there, or passing along values in a way that won't cause SQL injections. So the nice thing about prepared statements is that they separate the SQL commands from the input data. And so then it's a lot less likely that you're going to have malicious data that actually has harm. It does harm. And this gives you security, right? Because the data itself is validated, or at least is properly escaped when it is actually executed by the database. And if you have a SQL operation that you're going to execute a number of times, prepared statements can provide some nice optimization, because the database knows that it's going to perform this operation a bunch of times. It can optimize things in terms of how data is inserted, how data is batched together. Every application should use prepared statements for security, and then more advanced applications, or ones that deal with larger scale of data, can take advantage of databases' support for optimizing prepared statements. So far, we've seen examples of JDBC's statement class. There's also a subclass of that called prepared statement that lets you set query parameters on it. So here is an example of that same code that logs in an employee but uses a prepared statement. So now our SQL string doesn't have the name and password parameters in it. It just has question marks for what the name is and what the password is. And now we create a prepared statement from the database connection. And on that statement object, we set the first string, which is the name of the employee, and the second string, which is the password of the employee, and we execute that. And so now, because we use a prepared statement, the name and the password will basically have their values passed in directly. Will be properly encoded, maybe is a good word for it, when the query is ultimately executed. You'll still have select star from users, but here, if you pass in that malicious inputs, the admin will be properly escaped, so that that single quote after the n will be escaped as two quotes, and the dash dash will be considered text and text within that parameter and not part of the query itself. And more importantly, you'll still have the password equals foobar clause, and now you won't be able to. The query will not return the information about the administrator user. Do want to note syntactically that if you have two quotes together, that is basically a quote within an SQL string. So we've covered the foundational stuff about JDBC so far. There are some other things about JDBC that I just wanted to mention here. It's something that we'll be using in the class. Well, you probably will be using SQL exceptions, right? So if something goes wrong, an SQL exception will be thrown. You can get some nice information about what happened in the database, what the problem was from the exception itself. There's an error code that you can get, which is a vendor-specific issue. Plus, there's also standard SQL states that are available in the SQL exception. So you can get some more information, and database vendors will tell you, what it means to get error code 473. I mentioned before that there is a database metadata. There's also something called a result set metadata, which are objects that tell you about the JDBC either driver or the database schema or more information about the result set. Probably not stuff that you'll be using in your programs, but if you're using a tool that works with databases generically or generally, like a database browser or something that lets you modify the schema, those APIs come in very handy. And if you're familiar with something which is called a stored procedure, which is basically code that runs inside the database, JDBC does offer a callable statement, which is a subclass of prepared statement that can be used to invoke those stored procedures. It handles the in and out parameters that stored procedures have. Good stuff, but beyond the scope of this class and what we're talking about. Now, we've been talking about relational databases, and data in relational databases are tables, right? They're these rectangles, and they have foreign keys and primary keys that are used to relate data there. But just in terms of the image that you have in your head, it probably looks a lot different from Java objects, which are these I think of them as circles with lines between them. And while there's certainly some similarities, there are also some important differences too. And this really results in what's been called a paradigm mismatch between objects and tables. Objects are, you have classes, you represent the template that way, they have references to each other, you have collections of objects. These are sort of the native concepts to object-oriented programming. SQL has tables and keys and rows and columns, which, and while there's some similarities, there are also some important differences. And it's not always natural to go from one to another. So there is a set of tools called Object Relational Mapping Tools, or ORMs, that look to make it easy to take your objects and put them into databases, and similarly take information in databases and put them into objects. These are quite popular, and boy, I'm sure for almost every programming language has some sort of ORM tool or framework. The most popular one for Java is something called JPA, the Jakarta Persistence API. It used to be called the Java Persistence API. And what it does, it provides a standard API. This isn't JDBC, this is kind of on top of all of that map objects to database rows. And so what you can do is you can annotate your Java code, your classes, your fields with these annotations that are essentially hints to JPA that say, well, this is how this should be stored in the database. Or, hey, this field represents this column in the database. And then you've got JPA implementations like Hibernate or Spring Data JPA, which maybe you've heard of, that will essentially create all the SQL for you. And that's really nice. You don't need to write that SQL yourself. As you evolve your objects, the Hibernate will automatically update the SQL, even update the shape of the table. Good stuff there, but also pretty complex, and comes with some amount of overhead. But it's an important part of working with, I would say, professional Java applications with database persistence. So again, these ORMs are pretty nice because they remove a lot of the overhead code that, as you've seen, is required with JDBC. All those try-catch blocks, all of the handling of the results sets, making sure you've closed your database connections. Nope, you let the ORM take care of all of that. It's also nice that if you see an application that uses an ORM and you're familiar with that ORM, the code is so much more approachable than trying to figure out, hey, what kind of homegrown mapping code was used in this particular project. And so then this is why JPA has become so popular, because it really does offer a lot of power and in a standard way. However, there's definitely some downsides to working with ORMs and JPA. When something goes wrong, or when there's something that isn't easy out of the box, you need to understand sort of what JPA is doing behind the scenes, how JDBC works, all of those things. And that takes overhead, and that takes time to figure out. And depending on exactly what your application is doing or how your database is structured, that may be more effort than it's worth. Additionally, ORMs have been known to not be as efficient as they could be, which for small scale applications is probably fine, but as your application scales, you want to identify which points of it ought to be optimized to provide a better user experience. It can be hard to optimize queries when ORMs are involved because they own so much of the translation between the Java code and the SQL code. Now, we're not going to go into detail of JPA or other ORMs in this course. It's really beyond the scope of what I want to introduce, especially in this lecture. But I will say this, and professionally, hey, you might encounter these things, and you will do better. You will have a better experience. You'll be able to understand things a lot better if you are familiar with SQL, JDBC, and relational databases. So, JPA and ORMs is overkill for what we're talking about here. However, it's just a good design pattern to make sure that the code that accesses your database is appropriately isolated from the rest of your application logic. Do you really have to know that the object that you're working with is ultimately persistent to the database? Ideally not. And so when it comes to designing your applications, you want to make sure that your database code is appropriately isolated to reduce dependencies, to make it easier to update one side of the code, either update the database access code or to update the logic that uses the data that's persisted in the database. It's also a good idea to have it isolated so that you know where to look for your database code. If you see an exception or something and you say, oh look, that's from the database code, you have a better idea of what might be going wrong or where to go to look first to fix it. Also, by isolating your database code, it makes your application easier to test. You can mock out your database objects or the code that calls the database to make it so that you can still test your pure Java logic, even though in production, in the real world, there would be database calls involved. Because, of course, trying to test, automated tests with a database requires you to launch the database and manage the connection and everything like that. It makes it difficult to have quickly running unit tests when you have that much overhead involved. Also, if there's a new database vendor that you want to support, or maybe you're changing from one database version or vendor to another, by isolating the database code, it limits the blast radius, and so you'll know what code ought to change or is likely to change versus which code you don't need to look at for that migration. And so then all of this is related to the single responsibility principle of object-oriented programming. A class should have one reason to change, And so then the only reason the database access code should change is because of the database access. So something about the database or something about the code that's being persisted, that should be its only reason to change. If you are implementing, new logic in the UI or a new, I don't know, reporting or visualization scheme, your database code shouldn't have to change. So there's a simple pattern which offers some of the same advantages that an ORM does or JPA does, but it doesn't take over all of the database mapping itself. And it's called the data access object. And it's a pretty simple pattern. The whole idea is that it separates the code that models the data from the code that persists the data to the database. And the data is the role of the data is called a model. So this is a plain old Java object, a POJO. It has getters and setters and maybe a little bit of application logic, but not a lot. And it basically represents a row in the database. You can think of it that way. And so this is like your course class, right? There's a course instance that has a lot of the same information in the database. It has the name of the course and the number of credits, and it's modeled there in a plain old Java object. The interesting kind of the new object in this pattern is something called a data access object, a DAO. And this is the code that knows how to take your model, your course object, and persist it to the database. So this is the code that knows about the name of the table and the name of the columns and does all the JDBC work to invoke those APIs. And then the third player in this pattern is the application service. And this is really the client of the model and the DAO. So it's the thing that knows how to take a DAO, and often several DAOs for several tables or several kinds of data, and implement the application logic using the multiple DAOs to access multiple kinds of data. For instance, hey, in our university course schedule application, you can have a code that will use the DAO for courses and the DAO for departments to create some data and to correlate data together to query things and then put everything together and then ultimately serve up some result back to the user. And notice that in many of the examples of DAOs, there will be an interface for the DAO so that the persistence behavior implemented by the DAO can be mocked out really easily. And later in the course, we'll talk about mock objects and stuff, but you'll see that pattern in a number of places. So here is a diagram. This is not an entity relationship diagram. It's more of an object diagram that shows how multiple DAOs can work with each other to perform some application logic. So here again, hey, you've got an object that represents, that manages course offerings in our course model. There are, it can do things like, create a course with a given name for a given department, or, create a new course or add a course to a term. And again, what's inputted is not necessarily like the database IDs or even objects that represent all of these things. It's things like the name of a course and the name of a term. And then this course offering manager can then access the database through the database access objects, through the DAOs, to then abstract out all of that work. And so here's an example of like a course DAO. Well, what kind of objects do you have, or what kind of methods do you have in the DAO? Well, it'll have something that will save, a course object. So the DAOs usually work with the objects themselves, those POJO objects that represent data in the database. So you can save a course, you can look up a course by its title. Oh, you can find all of the courses in a department. You can delete a course, those kinds of things. And you can imagine there'd be similar methods on the department DAO and the academic term DAO, and then the course offering manager puts all that together. And here I'm representing the fact that the DAO itself is an interface which is then implemented by the DAO impl, and the DAO impl is the thing that ultimately has the connection to the database and will create the SQL statements and execute them, get the result sets back, create POJO objects like course, good stuff like that. Here's an example of one of those methods. Here's how the find by title method might be implemented in the course DAO impl object. Itself, the find by title method takes a string, which is the title, and returns a course object. So it creates an SQL statement. This is a prepared statement. And so we're selecting some columns from the courses table with the given title. And then we execute the JDBC code. we'll have a connection object. It'll be passing the constructor or something like that. We'll store it in a field. We'll use that connection object, call prepared statement on it, then configure the first parameter to the prepared statement, which is the first question mark. So that's the title in the query. Then we'll execute the query, get the result set, and then we won't show it here, but we'll extract the course object from the result set. You can imagine what that looks like. You go and look at each of the columns returned in the result set and populate a new course object from that. This example, we turn null if there aren't any results there. You could use the optional class, also optional object for this, and also I suppose you could have multiple courses with the same title. Anyway, in which case you return a list or a collection of courses. The bottom line here is that make sure your code supports what you need to support. This is a very simple example, so it would fit on the slide, but in the real world there are lots of things to consider when implementing your DAOs. Okay, we've talked a lot about relational databases. We've seen JDBC. There's one more topic that I want to cover, and that's some specifics about the H2 database. So in this course, when we write Java code and have it work with a relational database, we're going to use the H2 database. H2 is nice. It's open source. It's written entirely in Java, so there's no separate software to install. It's just another jar file that you download, and actually it's a nicely optimized jar file. It has a small footprint both from a disk storage space and also a memory. When it runs, it can run pretty efficiently in memory. And it's a full database, right? It conforms to SQL, it provides JDBC. It'll be really nice. And so I just wanted to say a few words about this so that you're familiar with it when you're using your projects. So H2 provides three modes of interaction. There's server mode, which is kind of the traditional way of running a database. It's a separate process from your application. You access it through a network socket using TCP/IP. You can have multiple clients all working with it at the same time. Really nice stuff. We won't be using H2 like that in this course. Instead, we'll be using it in the other two modes. So the second mode is an embedded mode, which means that the H2 engine runs inside your Java program. So you've got your application logic, and in the same process, you've got H2. Now, the data itself is persisted to disk, and so the H2 engine is sitting there writing to disk so that when your Java program goes away, the data is still there. You can start up and use it again. And that's embedded mode. H2 also supports something called in-memory mode, where H2, the engine, is running, but instead of persisting data off to disk, it just keeps it in memory, which is super convenient for writing tests. So, as your tests execute, they all work against data that's in memory. When the test complete, when the program goes away, so does all the data. There's nothing to clean up afterwards. So then, this is, we'll be using that for our unit tests in the course. So there are a couple of classes that I've written that I want to bring to your attention that help you work with H2. The first one is a class called H2 Database Helper. This is basically a class that will create the connection strings for H2. I provided this because I needed this, for the example code that I wrote, and I figured I'd tell you about it so you can use it too in your projects. There are two methods on H2 Database Helper. The first one is called create in-memory connection, and you give it a database name. This is good for unit tests. And here's the code right here. What I want to point out is that it uses driver manager.get connection, and the database name is just what's used in the connection string along with the mem mode. So you'll see the connection string is JDBC :H2 :mem and then the name of the database. We create the connection URL that way. And then there's also a parameter to the URL, the db close delay equals -1, which means if there are no connections to it, don't shut down the database right away. Leave it open because there might be other connections to be made. So that's the in-memory connection is used for testing. What will be used for your projects and saving the database off to a file that is persistent so you can see the results next time that your program runs. You'll use the create file-based connection method. And here it takes a Java IO file, which is the directory in which the database files will live, and that's how it creates the connection. So the way that the H2 operates, the way you distinguish about what mode the database runs and whether it's embedded or whether it is in memory is based on the connection string that is used to connect to the database. And I used air quotes around connect because in both these cases, the database itself is in the same process as the Java application. So again, I encourage you to use this H2 database helper class as you develop your database project and as you build the unit and integration test for it. The code that we just looked at is in the edu pdxcsjoy JDBC package in the examples project. There are two other classes that I want to bring to your attention because I'll be using these to create your projects. There's a class called print H2 database schema, which will take a file, a database file, H2 database file, on disk and print out descriptions of the tables that are in it. And there's also a class called execute H2 database statement, which takes again, location of a database file on disk and an SQL statement. I'll test it with selects, and it will query the database. It'll execute that statement against that database file. Now, I just want to give you a heads up that I'll be using these. I encourage you to take a quick look at them to understand what they're all about. You may also want to run them on the database files that are created by your projects prior to submitting. And if you do choose to run these programs, I want to remind you that you'll need to put the database driver on the class path. The nice thing about projects and the fact that H2 is so small and can be embedded is that the database driver, really all of H2, is downloaded in a single jar file, and that's where it lives on disk. That's, of course, for version 2.4.240 of H2. If we use a newer version, you'll have to adjust the directory path accordingly. Okay, well, and that's it. So we covered a lot here, and it was all about JDBC working with relational databases with Java programs. And so the JDBC API is a standard interface that all Java programs can use to work with relational databases. A key aspect of JDBC is that there's something called a driver, which is Java code that provides a bridge between the standard JDBC API and whatever mechanisms an individual database vendor uses to access their database. There are some foundational classes in JDBC that you should know about. There was the connection class that represents the connection to the database, a statement for executing a SQL statement, and then a result set, which is what you get back from a query. We learned about prepared statements, which is a way to protect your programs against SQL injection attacks and offer some optimization. But primarily, you should be using prepared statements to make sure that the data that is passed to your query is actually the data that you intend. And then we also talked about things like the fact that SQL maps the types of SQL database columns to standard Java types, things like big decimal and timestamp. And we also talked about how the data access object pattern can be used to separate the code that works with the database from the rest of your program. So other application logic that's really best served by focusing just on what it does well. Finally, I did want to call out some of the sources and references that I used putting together this content. I highly recommend the JDBC tutorial from Oracle's website. It covers a lot of good foundational stuff, as do these other resources. And I wanted to call out that I did use both Google Gemini and GitHub Copilot for AI-assisted research. And so that's it. We've covered a lot of ground with relational databases. I hope that you found the information that we talked about to be compelling and relevant to what it is that you're doing. And as always, thank you for exploring contemporary software development as part of the joy of coding here at Portland State University.